Now, remember I say that preparation of salts largely depends on whether the salt is soluble or not in water. Let us begin to see how salts can be prepared. So the first category of preparation of salts is known as preparation of soluble salts. And these ones can be prepared by the following methods: reaction of acids with metals, reaction of acids with bases, which is neutralization, and the reaction of acids with metal carbonates or hydrogen carbonates. Now all these we have already done from our Form 1 work and Form 2. So it is going to be very easy. Next is the preparation of insoluble salts. Now here we learn something new known as double decomposition or precipitation reactions. And finally, direct combination of elements, which is direct synthesis, which is nothing new. We have already done this before. So basically, salts is the easiest topic because it's a revision of many things we have done. Referring back to Form 1, we made a very good discovery that when metals react with acids, they form a salt and hydrogen gas. So this is a method that you can use to form salts. One of the salts that can be prepared using this method is calcium chloride from calcium metal and dilute hydrochloric acid. The procedure for this preparation is as follows. First, you add excess calcium to dilute hydrochloric acid in a beaker and stir with a glass rod. There will be effervescence, that is the indication for the evolution of a colorless gas. But we are not really interested in the gas today. Today we are interested in the salt. Secondly, you filter the mixture to remove excess calcium and pour the filtrate, which is calcium hydroxide, into an evaporating dish. Then you heat the solution to saturation, then allow it to cool to form crystals. You filter to obtain crystals as a residue, and finally dry the calcium chloride crystals between filter papers. As you can see, from procedure number 3, it is the procedure for crystallization that we just did a few moments ago. The equation for this reaction is as follows. There are many other salts that can be prepared using the reaction between acids with metals. These include the following reactions for the preparation of salts. Zinc chloride can be prepared using this reaction, but the procedure is exactly the same like the one we have just described with calcium and dilute hydrochloric acid, but this time we'll use zinc instead of calcium. Again, zinc sulfate can be prepared using this method, and this is the equation for the reaction. Similarly, magnesium chloride can be prepared using this method. Magnesium sulfate can also be prepared using this method. Can you think of other salts that can be prepared using this method? Can we prepare copper 2 chloride using this method? Try to find out. Next, we can still prepare soluble salts using the reaction of acids with alkalis, or which we call neutralization reactions. For example, the procedure of preparing sodium sulfate crystals from sodium hydroxide, which is an alkali, and dilute sulfuric 6 acid, which is an acid. First, you add about 20 cubic centimeters or milliliters of dilute sulfuric 6 acid in a conical flask and put a few drops of phenolphthalein indicator. Then, using a burette, you add dilute sodium hydroxide solution to the conical flask carefully until the solution just turns pink. This should be done as you're shaking or swirling the conical flask to ensure that the two solutions mix completely. Next, you heat the solution to saturation, then allow it to cool to form crystals. Filter the mixture to obtain crystals as a residue. And finally, you dry the crystals between filter papers. The crystals will be sodium sulfate crystals. As you can see again from procedure 3, it is the process of crystallization. The equation for that reaction that is taking place is the following. This is a neutralization reaction. There are a myriad of salts that can be prepared using this method, but mostly the ones of metals which are high in the reactivity series are best prepared using this method, because metals that are high in the reactivity series cannot be reacted directly with acids. For example, potassium hydroxide reacts with dilute sulfur hydrochloric acid to give potassium chloride and water. Next, we can prepare ammonium sulfate using this method. We can also prepare sodium chloride using this method. Next, it is the preparation of salts using the reaction between acids and bases. Now remember, there is a difference between a base and an alkali. In the previous reactions, we were dealing with soluble bases, which are known as alkalis. I hope you remember, an alkali is a base that is soluble in water. So the preparation of copper 2 sulfate crystals from copper 2 oxide, which is a base that is insoluble in water, and dilute sulfuric 6 acid. The procedure is to add excess copper 2 oxide to warm dilute sulfuric 6 acid in a beaker. Remember, the dilute acid should be warm to increase the rate of reaction. Stirring may also be helpful. Filter the mixture to remove excess copper 2 oxide and pour the filtrate into an evaporating dish. Next is the crystallization process. And the equation for that reaction is as follows. The other salts that can be prepared using this neutralization process are as follows. Magnesium oxide is a base, but it is insoluble in water. We can also use this to prepare calcium chloride, lead 2 nitrate, and many other salts. Remember, the distinguishing factor is that the base is insoluble in water. Again, we can use carbonates or hydrogen carbonates to prepare salts. I'm sure you remember that the products when a carbonate or a hydrogen carbonate react with an acid is a salt, water, and carbon 4 oxide. However, today we are interested in the salt that is formed. The procedure is very easy, as follows. You add excess lead carbonate to warm dilute nitric 5 acid in a beaker and stir with a glass rod until effervescence stops. Effervescence is the indication that a gas has been produced, and this gas will be produced until all the acid has reacted with the carbonate. But after that, when the reaction is over, no more gas will be formed. So this time, the effervescence is our indication that the reaction is going on. When it stops, the reaction is over, and we'll be sure that all the dilute acid has reacted with the carbonate. I'm sure by now you can tell me the next step. Aha, you said filter the mixture to remove unreacted lead carbonate and pour the filtrate in an evaporating dish. Remember, the filtrate is lead nitrate solution. Then next, you heat the solution to saturation to allow it to cool. Then you filter to obtain crystals, and then dry the crystals between filter paper. The equation for this reaction is as follows. Once again, other salts that can be prepared using the reaction between carbonates or hydrogen carbonates with acids are zinc nitrate. Zinc nitrate can be prepared by the reaction between zinc carbonate and nitric 5 acid. The next one is ammonium sulfate. The equation is there. We can also prepare sodium phosphate from the reaction between sodium hydrogen carbonate plus phosphoric acid, which will give us sodium phosphate, water, and carbon dioxide. Be keen on how to balance this equation. Now that you have already learned how to prepare soluble salts, let us go to insoluble salts. Insoluble salts are prepared using double decomposition or precipitation reactions. Now, let me just recap on something that we did while you're still in Form 1. When you're in Form 1, there is a time we learned about the competition for oxygen. We learned that some metals react more vigorously with oxygen than others. More so, some metals can remove combined oxygen from other metals. That was an example of a decomposition reaction. It was a displacement reaction where one metal displaces oxygen from another. In this case, we advanced the same procedure, but this time, instead of using a metal and a salt, we now use two salts. So let us go right in. Preparation of solid lead sulfate from lead nitrate and potassium sulfate. Now remember, these are solids. The first step is to add about 25 milliliters of water to solid lead to nitrate and solid potassium sulfate in separate beakers and stir with a glass rod to dissolve all the solid. This one will lead us to two solutions, one solution for lead to nitrate and another for potassium sulfate. The next procedure is to add lead to nitrate solution to potassium sulfate solution and stir with a glass rod. You will notice that a white precipitate will be formed. That white precipitate is lead sulfate. That precipitate is filtered off from the mixture and obtained as a residue, and finally we dry the solid between filter papers. Now the reason why this is called a double decomposition can be understood by looking at the equation. Now when you look at this equation, lead nitrate reacts with potassium sulfate, and something interesting occurs. The metals exchange the radicals. Lead, which contained the nitrate, now contains the sulfate. Potassium, which contained the sulfate, now contains the nitrate. They have exchanged the radicals. And this process where two salts exchange their radicals in solution is known as double decomposition or precipitation. Now there's something else we need to learn from this. It is known as writing ionic equations. An ionic equations only considers the active part that is taking place. The first thing we do is to split the aqueous solutions into their respective ions. For example, lead nitrate solution contains lead 2 ions and nitrate ions. Potassium sulfate solution, on the other hand, contains potassium ions and sulfate ions. Now, when we get to the solid, we cannot split it because it is not in aqueous solution. We only split the compounds that are in aqueous solution. Then, potassium nitrate contains potassium ions and nitrate ions. When you look at this equation, we have ions that appear on both sides. For example, nitrate ions appear on both sides of the reaction. Again, potassium ions appear on both sides of the equation. These are called spectator ions because they don't take part in the active formation of lead sulfate. And hence, we cross them out as follows. Cross the nitrate, cross out the potassium ions, and we are left with an ionic equation. Lead ions reacting with sulfate ions to give lead sulfate. And the final equation is written as follows. It requires quite some practice for you to get it, but don't worry, you can always repeat the procedure as many times as you wish until you get the hang of it. Again, other salts that can be prepared using double decomposition or precipitation reactions include barium sulfate. See, it is an insoluble salt. Once you realize that you're preparing an insoluble salt, you first of all just think about double decomposition. In this case, we will use two solutions of barium nitrate and sodium sulfate. Remember, if these two salts are given in solid state, we will have to dissolve them in water before we can carry out double decomposition. It is also important to note that the two salts that are used in the preparation must be soluble in water. So the reactants must be soluble in water for this reaction to take place, so that the ions can be split in water. The process of splitting an ion in water is called dissociation. So the ions will be dissociated in water, and therefore they are able to move about and reorganize themselves to form the products. The ionic equation of this reaction is written as follows. And again, another salt that can be prepared using this method is lead to iodide. This is a spectacular reaction, like the one, remember the one I told you about, golden rain in the beginning of this chapter? Yes, that was the preparation of lead to iodide. Lead to iodide is yellow in color, and that is why we call it gold rain or golden rain. So you see, precipitation reaction means rain, and then yellow is the color of gold, so it is gold rain. The ionic equation is as follows. There are many other ways or many other salts that can be prepared using this method, so long as remember that we must be forming an insoluble salt. And this insoluble salt must be formed from two soluble salts. Well, that's it. Thank you. Welcome back. Preparation of salts using direct combination of elements, or rather we call it direct synthesis. Again, I take you back to Form 1. I told you this topic relates a lot with what we have already done. In Form 1, when we are talking about elements, the constituents of elements, we said that a compound is formed when two elements combine chemically. And the example that we gave was iron reacting with sulfur to give iron 2 sulfide. That was an example of preparation of a salt known as iron 2 sulfide using direct synthesis. Now, let us see how another salt can be prepared using a similar method, the preparation of sodium chloride from sodium and chlorine gas. Chlorine and sodium are elements. They are the constituent elements of sodium chloride. And therefore, we want to know how we can prepare it. The first step is to heat a small piece of sodium in a Bunsen burner until it begins to burn. Then we lower it in a gas jar full of chlorine gas, and a reaction that is spectacular will happen. Sodium will burn in a bright yellow flame, and it will form white fumes of sodium chloride. You allow the setup to cool and collect the white crystals that are formed in the end. The crystals formed will be very tiny, so don't expect to find a salt that is the one that you see in the kitchen. However, through crystallization process, we can increase the size of crystals. The equation for the reaction is very simple. Once again, other salts that can be prepared using direct synthesis include iron 2 sulfide, iron 3 chloride, magnesium nitride. Can you try to describe experiments for the formation of these three salts? I guess you can. The knowledge of salts is very important in our daily lives. Some of the uses of salts are in the manufacture of fertilizers such as DAP, which is diammonium phosphate, calcium ammonium nitrate, which is CAN, and ammonium nitrate fertilizers. As you know, fertilizers are very important because they help in agriculture and food production. Next, potassium nitrate is used to make gunpowder and fireworks. Spectacular fireworks used during celebrations are a result of the knowledge of salts. So potassium nitrate is very important. Many salts are used in defrosting snow in winter. Like you see in this diagram at the far right side, there are cars in winter and there's snow all over the road. So salts are added to ice or snow as an impurity to lower the melting point so that it can defrost faster. Calcium chloride is used during the extraction of sodium. This one is also an impurity that is added to molten rock salt in order to reduce its melting point and therefore reduce the amount of heat used during the process, saving a lot of money. Calcium chloride is also used in road surfacing. Here, calcium chloride is used to keep the road moist due to its deliquescent nature, and moisture absorbs dust. That is why when you're driving on a tarmac road, you cannot find dusty roads. Sodium chloride is used as a food additive. This one everybody knows. Also, some salts such as lime are used to neutralize soil acidity. Lime is basically calcium oxide. Some of the properties of salt that is important is the exposure of salt to the atmosphere. Some salts exhibit these unique properties, such as deliquescence. When we were talking about the use of calcium chloride, we mentioned that it keeps roads moist because of its deliquescent nature. Deliquescence can be explained using the following. When calcium chloride is left exposed to the atmosphere overnight, it forms a colorless solution. Similarly, when shiny black crystals of iron 3 chloride are exposed overnight, they form a yellow solution. This process is known as deliquescence. Hence, deliquescence is the process where a salt absorbs moisture from the atmosphere and goes into solution or dissolves in the water. The next interesting property is known as hygroscopy. When anhydrous copper 2 sulfate is left overnight exposed to the atmosphere, it will turn from white to blue and becomes damp. In a similar way, anhydrous cobalt 2 chloride will turn from blue to pink and becomes damp. Remember, these two salts do not dissolve in the moisture that has been absorbed, and therefore hygroscopy is the process where a substance absorbs moisture from the atmosphere but does not go into solution. Another unique property is called efflorescence. Consider the following. When hydrated sodium carbonate decahydrate is left exposed to the atmosphere overnight, they form white powder of sodium carbonate monohydrate. Don't be scared about the terms. This equation will make it easy. Sodium carbonate decahydrate means it has 10 molecules of water of crystallization. And monohydrate means it has 1 molecule of water of crystallization. In this case, sodium carbonate decahydrate has lost water to the atmosphere, and the molecule of water that has remained is only 1. And therefore, efflorescence is the process where a salt loses its water of crystallization when exposed to the atmosphere. Another example that is very similar to this one is this. Alright, these are the unique properties of salts. Better remember them because they are very important. The action of heat on salts can be divided depending on the categorization of salts. For example, carbonates behave in a different way from nitrates and sulfates. So let us consider carbonates. Pure carbonates of potassium and sodium are not affected by heat, but hydrated sodium carbonate and potassium carbonate give off the water of crystallization on heating. The following equations will explain. Other metal carbonates decompose to give off a colorless gas and a metal oxide. You will notice that this colorless gas forms a white precipitate with lime water. Do you remember the gas? Let us consider these equations. For the case of ammonium carbonate, it decomposes into ammonia gas, carbon 4 oxide, and steam. Ammonium carbonate is unique, so better remember this unique property. The equation for that reaction is as follows. Since it's the first time I think you're meeting ammonia gas, then you better remember the formula. It is NH3. It is actually derived from the ammonium ion right here. When we come to nitrates, the nitrates of potassium and sodium, since you have noticed that sodium and potassium are high in the reactivity series, decompose to give their corresponding nitrites and oxygen gas. Use these equations to consider these reactions. Well, the nitrates of other metals that are in the middle of the reactivity series, in this case, will give off a colorless gas, a brown gas, and a metal oxide. Do you remember the permanent changes in Form 1? At that time, we heated copper nitrate. What were the products? I guess you said these products. Nitrogen 4 oxide gas and oxygen gas plus a black solid of metal oxide. So basically, copper 2 nitrate is usually blue, green in color, and copper 2 oxide is black. This is the brown gas and the colorless gas. Another example is lead nitrate. It decomposes to form lead oxide, nitrogen 4 oxide gas, and oxygen gas. Calcium nitrate decomposes in a similar manner according to this equation, as well as zinc nitrate. As you can see, these reactions are very similar to each other. And finally, metals that are low in the reactivity series form nitrates that decompose to give off a colorless gas, a brown gas, and a corresponding metal. For example, silver nitrate decomposes on heating to give silver metal, nitrogen 4 oxide, and oxygen gases. In a similar way, mercury nitrate decomposes to give mercury plus nitrogen 4 oxide gas and oxygen gas. Ammonium nitrate decomposes very uniquely into nitrogen 1 oxide and steam. Using the following equation, we can picture the reaction. Ammonium nitrate is a solid which decomposes to form steam and nitrogen 1 oxide. Take note of how we write nitrogen 1 oxide. Next, let us look at the action of heat on sulfates. The sulfates of potassium, magnesium, calcium, and sodium are not affected by heat, but if hydrated, they will lose their water of crystallization. Consider the following. Other metal sulfates usually decompose to give a colorless gas that turns moist blue litmus paper red and a corresponding metal oxide. In this case, zinc sulfate decomposes on heating to give zinc oxide, sulfur 4 oxide, and water. This water essentially is just the water of crystallization. If this salt was anhydrous, then it would not be having any water. Again, copper 2 sulfate, hydrated copper 2 sulfate on strong heating will decompose to copper 2 oxide and will form sulfur 4 oxide gas. This is the gas that turns moist blue litmus paper red, meaning that it is acidic in nature and somewhat of crystallization will be released. Remember, this one is black in color, while copper 2 sulfate, hydrated copper 2 sulfate is usually blue. Next, hydrated iron 2 oxide decomposes in a unique way to form the following products. It decomposes to form iron 3 oxide, sulfur 4 oxide gas, sulfur 6 oxide gas, and the water of crystallization. Now you see it forms a mixture of two gases, sulfur 4 oxide and sulfur 6 oxide. And remember also, iron 2 sulfate forms iron 3 oxide. Those unique properties that you need to be very keen not to forget. Again, we come to the close of this chapter. We've been used to reviewing chapters, but this time you will review it yourself. Describe how to prepare solid samples of the following: lead carbonate from lead metal, nitric acid, solid sodium carbonate. Think about the salt and the materials that you've been given, then devise a procedure. Also, think about how you can prepare iron 3 chloride from iron metal and chlorine gas. Interesting, right? Then I need you to describe a test that can be used to find out if Nairobi River is contaminated with harmful lead compounds. Well, that's it. See you next time.